So, okay,
Let's start. Hello everyone. Thank you for being here. My name is Wenyan Chen. I'm a final year PhD student in the University of Macau, and I'm co-supervised by Professor Huanle and Professor Kejiang. Today, I'm excited to share our work, Multiplexing Dynamic Deep Learning Workloads with SLO-awareness in GPU clusters. This is a joint work with my colleagues, Dr. Chengzhi and Professor Chengzhong. Deep learning services are becoming increasingly popular in our daily lives, and GPUs are widely used as inference accelerators. When a user submits a request, the inference service is expected to respond within a specific time limit, such as 30 milliseconds. This is the SL requirement for each inference request, which typically includes the waiting time and the execution time. To enhance the performance of inference serving, batching is employed to process multiple requests at the same time. First of all, let's see how inference behavior in the GPU clusters. We analyzed the inference traces from Alibaba for a day. We can clearly see from the first figure, the inference requests for inference A and inference B is very fluctuating and unpredictable over time. In the second figure, we can clearly see that the GPU resource is underutilization and over-provisioning. Therefore, to improve the GPU utilization, the cloud managers often packing multiple tasks on the same GPU via time sharing or spatial sharing. While time sharing is rounded-based interleave execution of various tasks, and it can increase the GPU utilization by reducing the idle GPU cycles. However, it still utilizes the spatial resources. For spatial sharing, there are two typical methods of NVIDIA GPUs. The first is MPS. It can allocate logical GPU partitions for various tasks, and the allocations are very fine-grained, which ranging from 1% to 100%. The second is MIG. It can allocate physical SM cores and memory to each multiplexing task. But the allocation strategies are very limited, and it needs to restart all instances when the strategy changes. Therefore, MPS is less flexible and higher cost. MIG is less flexible and higher cost. MPS becomes a better choice compared with others. However, there is a question here. Which task type is better to be multiplexed with inference? Is inference or training? We conduct some experiments to answer this question. Firstly, we break the execution process of inference. It can be split into three stages: tokenize or data preprocess, data transfer, and inference. Then, we analyze the end-to-end interference and break down the interference of two cases: multiplexing inference with inference and multiplexing inference with training. As we can see in these two figures, the end-to-end interference is a little larger, which is up to 3.19 times. However, when multiplexing inference with training, the interference is a little small. It's below 1.67 times. Therefore, we can get the observation that the end-to-end interference on inference is smaller when multiplexing inference with training. We give an in-depth analysis of the reasons from the following aspects. For tokenize or data preprocess, it is parallel, which requires substantial CPUs for execution. This will lead to severe CPU contention. For data transfer stage, the frequency of data transfers required by training is less than that of inference. For inference stage, the control flow accounts for up to 72% of the total execution in the inference stage. This stage will also lead to CPU contention. Additionally, we also found that the GPU and memory utilization is high when inference is multiplexed with training. Therefore, multiplexing inference services with training tasks is more beneficial. However, when inference is multiplexed with training, it raises another critical question. How can we maintain the low latency for inference and high throughput for training at the same time? To achieve this target, there are three main challenges. The first is the dynamic workload arrivals, such as unpredictable KPIs for inference and unobserved training tasks arrivals. The second is the intricate coupling between the cluster-level task placement and the device-level parameter configurations. The third challenge is the large optimization space, which often includes three important factors: the packing patterns, the SM percentage, and the batching size. We need to find the global optimization from them. To address these challenges, we propose a new system which named Mudi. It is a multiplexing system for highly dynamic deep learning workloads that prioritizes SLO-awareness for inference services. In Mudi, there are two key ideas to drive our design. The first idea is to explicitly model inference latency. Latency is a function related to collocation, batching size, and GPU percent. By quantifying latency precisely, we can design effective resource scaling and adaptive batching policies. This makes it much easier to evaluate whether the inference SLOs are being met. The key observation here is that the latency and the GPU partitions follows piecewise linear functions, and both the solo run case and the co-run case. This idea can address the large optimization space while considering both the cluster-level collocation and the device-level interference control. The second idea is to use the underlying network architecture to estimate the slope of the piecewise linear function in advance, which is based on the offline profiles. This approach can be adapted to dynamic training workloads. Based on the key ideas, we built the system architecture of Mudi. It contains three important components. The first is offline profiler, which profiles the interference latency curves of co-located tasks. The second is the online multiplexer. It records the requests and makes packing decisions. The third is the local coordinator. It monitors the KPIs for each inference service and updates the configurations such as batching size and GPU percent online. For inference latency profiling, we use offline samples to construct piecewise linear functions for each inference task, which is multiplexed across different training tasks. This approach is very efficient while just using a few samples to capture the relationship. It's faster and more accurate than polynomial and machine learning-based methods. For online prediction, we import the network layers, their types and numbers, and the configurations, such as batch size and the GPU percent, into the predictor. And then Mudi trains the predictor using these samples. Finally, the online multiplexer utilizes the trained model to forecast the interval latency of inference services. We can formulate an optimization model with the goal of minimizing overall training time of all co-located training tasks on each device, while ensuring the inference SLOs are being met. To achieve this, we need to solve for three key variables in this problem: the placement, the GPU percent, and the batching size. Yeah, it's an NP-hard problem, so we tackle it using a heuristic approach. Usually, model type is regarded as the most critical factor affecting interference. So we started by solving the placement variable. As you can see in this figure, when a user submits a training task, the online multiplexer fills out the available GPUs that has no training tasks. Then it uses the predictor to estimate the interference on each GPU device. And finally, the device selector will place the training task on the optimal GPU device with the smallest predicted interference. After placement, here follows the device-level multiplexing. But for most cases, we don't need to adjust both the batching size and the GPU percent. Based on our observation, the batching size has a bigger impact on running efficiency. So when the KPIs changes a lot, we start tuning batching size first. We solve this problem with GPLCB. It's a black box build method that can figure out how batching size and the objective function interact, which is just based on the real-time based feedbacks. If changing the batching size is not enough, we use a resource scaling approach to adjust the GPU percent. Since we have already figured out the placement and the batching size, we just need to find the optimal GPU percent. We can do this by solving a minimization problem with CVXPY. The soft GPU percent is for inference, and the remaining GPU partitions are for training. However, when updating GPU percent, MPS needs to restart the process to update the environment variable, which can cause much overhead. We use shadow instance to solve this issue. As this figure shows, after we found the optimal GPU percent, we set up a shadow instance. Once the shadow instance is ready for handle requests, it takes over as the active instance, and the old active instance will be destroyed. We also analyzed the MUDI's optimality. The experimental results show that MUDI can identify the optimal collocation with a high accuracy. Furthermore, the iteration time is bounded by 1.1 times, and the SLO violation is bounded by 1.08 times. These results prove that MUDI is very close to the optimal solution. Moreover, MUDI can be extended to be multiplexed more training tasks with one inference on the same GPU. The training tasks are no more than 3, as more training tasks will lead to performance degradation, as analyzed in our previous work at Deep. We can profile more samples and designate the cumulative feature layers of all multiplex training tasks as phi. And finally, we can evenly distribute the remaining resource partitions to each training task. However, when tuning batching size for inference, there may occur out-of-memory issues. Therefore, we design a memory manager which can dynamically swap memory between the GPU and the host for training tasks. This is a middleware between the deep learning workloads and the GPU dynamic link libraries. This is implemented based on the CUDA Unified Memory API. To evaluate the performance of MUDI, we use a physical cluster with 12 A100 GPUs and simulated an 1000 GPU large-scale simulator cluster as the test base. The baselines are GSLAS, MuseFlow, and GPULAS. The deep learning workloads are shown in these two tables, and the training task arrival rates follows the Microsoft trace. The end-to-end performance shows that MUDI performed best in both small physical cluster and large-scale cluster compared with the SOTA baselines. The SLO violation is reduced by up to 6 times, and the training efficiency is improved more than 2 times. Additionally, we also evaluate the simulator's fidelity of MUDI and the optimality of MUDI using the real-world experimental results. Moreover, with MUDI, GPU utilization in the physical cluster is improved, and the max system throughput increases with SLO compliance. Additionally, MUDI is capable to handle heavy loads, and the system overhead of tuning and packing is very low. There are more evaluations which you can refer to our paper if you are interested. To conclude, we solve a problem that how to maintain the low latency of inference and high throughput for training at the same time. The key insight we found is that multiplexing training with inference has much lower interference on inference services. We also propose 2 key ideas to address this problem. The first is accurate modeling of inference latency using piecewise linear functions. And the second is predicting the interference based on the underlying network architectures of training tasks. The experimental results show that MUDI can reduce CT of training by up to 2.27 times with satisfying the SLS for all inference requests. That's all for my presentation. Thank you for your listening.
Okay,